So let's get started. Hello, everyone. My name is Charlie, and I've just recently obtained my PhD at the University of Toronto in a machine learning group. So so today I wanted to talk to you guys about how do we do deep learning with structure. So I'm sure earlier in the day you guys have heard a lot about how you can use deep learning and some of the tools that you can use, but essentially deep learning is neural networks. And so with deep learning, that there's lots of buzz recently that's been sort of generated, so the thing is that in vision, speech, and natural language processing, discriminatively trained networks are found to achieve very good recognition rates, from ImageNet to speech recognition on your Android phones and Siri, things like that. However, we're still not there yet. We're not where we would like to be in terms of semi-supervised and unsupervised learning. So today I'd like to talk to you guys about three different models, specifically related to generative learning. In this case, the first one is the robust Boltzmann machine, and the second model I would like to talk to you guys about is what's called deep Lambertian networks, and the third one is learning with visual attention. So for the robust Boltzmann machine, the question is, how do we better deal with noise inclusion? And this is relevant to lots of recognition problems, because the scene in our environment is often very cluttered with occlusion. So anything you see, it could be partially occluded. There could be noise due to, for example, noise in the environment due to illumination variations and so on. So how do we handle that? So I'll skip the math for now, but I'll give you an illustrative example. So in this case here, if we have a face model, then the log probability assigned by the model on the face is highest. So here's in nats. So basically, the higher number, the better. However, on the left image, it's negative 551. However, if we block it with some sort of occlusion, and we see that the log likelihood dramatically decreases. So, and basically, what this is saying is that the model does not know what's going on. The density assigned by the generative model, probabilistic model, suffers a lot, even though we're simply occluding only a fourth, the left or the right quadrant of the face, and the rest are completely visible. And this just demonstrates that the model is not robust to occlusion, which can happen a lot. For example, due to sunglasses, due to the scarf, and so on. So how do we handle that? Well, we employ a generative model called the robust Boltzmann machine, and this is this is a generative model that's been developed for maybe 15 years now, and the idea of this is actually one of the sort of precursors to deep learning, the revival of deep learning. And this is a bipartite Markov random field with binary latent variables. And if you look at the figure in the middle, we have visible units that corresponds to pixels. And then we have binary hidden variables, which sort of, you can think of these as features. There's edge features or corner features or parts of an object. And so this is the model that we're going to be working with. This is it's generative, so that means that the model can assign probabilistic density to the data. And so how do we handle this? So how are we going to handle this case here? Okay, so in this case, the right thing to do is basically we need to add a set of masking latent variables. As you see on the right, we have a set of white, indicating that we're clamping on the white region, which means by clamping, I mean take these values as clean pixels, clean image, and not change them. And we want to impute, basically fill in the black region, because this is noisy area. So that's the solution we want to do. So mathematically, what we have to do is we have to make a modification to the existing network. In this case, we're adding 3 sets of pixels to each of the original pixel, so you see on the right, and essentially what that does is it adds a set of latent binary mask variable to the model. On the left panel, you see that the V tilde represents the noisy image of a person with the white block occluding the right eye. V and S these are latent variables. So the model does not have, by latent I mean the model doesn't know what their value is. A priori, it has to figure out what they are, and the model then uses prior by learn on thousands of other faces, distribution of what faces look like, to then interpret to infer what a clean face will look like. And the reason we want to infer what the clean faces look like is that would be very helpful for recognition. So this is the basic model that we're going to be working with. And as you see here, if you look at the structure of this model, this is going to be a slight modification to the original restricted Boltzmann machine. And I'll show you some of I'll skip the math and I'll show you some of the cool effects that we can do with this model. So here, here's an image of what happens to the model during training. Let's look at the top panel here. The top row of the top panel is shows the training data, which is a person with a specific type of occlusions, a grid of 3x3 noisy block. And the middle row and the bottom row, the V and S, these are inferred. So the model figures out by itself what the person will look like under the sort of the clean version of it. And then the bottom row, the S, is actually the learned structure representation of the noise. So initially it has no idea what the noise will look like. As learning progresses, it eventually figures out that the noise will probably look like a 3x3 grid of a block. And you see there's some salt and pepper noise there, because this model is fully probabilistic. And we use skip sampling, which comes from it's a sort of a MCMC sampler doing learning and as well as inference. So we have some noise because the entire model is stochastic and not deterministic. Same thing for the bottom one, the sunglasses, because the model it's trained on faces without sunglasses, so it has no idea what it thinks sunglasses is not a particular typical face. So what it does is it sort of removes the sunglasses for you. Some other examples. This is we can use the model for denoising and removing occlusion, and it works better than other models such as the simple RBMs, PCA, Wiener filtering, nearest neighbor. And the reason it works better is because we added the additional complexity or multiplicative gating so that we can actually gate off the noisy areas. And this requires no human intervention in the sense that we don't have to tell the model where which pixels are noisy and which pixels are clean. It just figures out by itself using its prior. Same thing for removing noise. So the original noisy, and then our model can remove noise very efficiently. And here's some quantitative data that shows that recognition accuracy improves when you first remove the sunglasses or scarf, and then you classify based on the clean image. Okay, so that's a very simple. So what I just talked about is a very simple way of adding a little bit of complexity to allow us to be able to handle occlusion and noise, which exists in the real world environment if you want to use these models for recognition. Another source of variation is noise illumination variation, right? So, from indoor to outdoor, from lighting comes from different directions on person's face. And we know that lighting variation is very detrimental to accurate recognition. And so how do we actually add more structure to generic neural nets, which are simply, these artificial neural nets are simply distributed representations of linear transformations followed by nonlinearities. But we want to be able to add some structuredness to it to allow it to handle better handle illumination variations. And so our solution is to add these things called albedo and surface normal and lighting hidden variables to our model. Albedo is sort of the surface reflectivity of material, like a paint. Surface normals are essentially vectors which are perpendicular to the local surface tangent. Specifically, here's the model that we take inspiration from. It's called a Lambertian reflectance model. What it says is that if you have a 3D surface, the lighting that strikes the surface, the angle of that vector and the surface normal, the cosine of that angle is proportional to times albedos is going to be proportional to the intensity that a camera might capture. This is the physics-based model, and what we do here is we put this operation, if you will, the Lambertian assumption, into a deep leaf network or a deep Boltzmann machine. And so here you see that the part that's circled in red is the albedo deep Boltzmann machine. So it's a generative model of what a face will look like under no illumination variations. A deep Boltzmann machine, for those of you guys who might not be familiar, is think of it as just like a complicated nonlinear mixture of Gaussians. So it's just a probabilistic density model. In the middle here, we have another deep Boltzmann machine modeling the surface normals, and it displays 3 channels because surface normals is a 3 vector. And then we have a Gaussian modeling the lighting direction. So essentially, this is what we're trying to do is inverse graphics in a certain sense. And these 3 representations combined will give you a face under different lighting scenarios. Like all machine learning algorithms, we need data. So this is trained on face, the ELB face data set with 38 subjects. And as you can see here, some of the faces have heavy illumination variations. So we train our model on this. Training is done in stochastic fashion, and after training, I'll show you some of the cool things we can do. Here, so what you can do is you can take a test subject, V, image of a test person. By test, I mean this particular subject was never seen before during training. So we take one of his faces where there's shadow across the top left part, and then we put it into the net and we do inference. So doing inference, by inference, what I mean is that the model only sees one image, and it has to try to figure out what the albedo, which is just lighting, the image of this person without any lighting variation, and a surface normal will look like, just by only one image. And typically this is known as the ill-posed problem in vision, because there could be multiple solutions to synthesize V. But however, because the fact that we're using a deep generative model that has a prior, this gives us extra constraints in a probabilistic sense. So we can actually come up with a unique solution that's coherent with the prior of what typically faces look like and typically what prior surface normals would look like. Okay, so the top row is the albedo that's inferred, and the bottom row is the surface normal. So initially at time step 1, it just has a mean face. That's the initial conditions, the initial step. But then as we run the Gibbs chain for sampling from the posterior of this distribution, we come to a male face, and then the surface normals is plotted as a color image because again it has a sort of 3D vector per pixel location. So here it quickly, after 10 Gibbs chain iterations, quickly jumps into the correct mode, which is what it should be doing. Another cool thing we can do is is once we figure out the albedo and surface normal, because we have a Lambertian generative assumption, right? We can actually do relighting, or what that means is that actually synthesize new novel images of this particular person by changing the light directions, right? So if you look at the top row, the image of this person is basically the light comes from sort of a lower left. But then these images generated on the right, we can have a more extreme lighting variation, such as the third image over. You can see the light comes from the way to the right. So, and these are completely synthesized by our model. And this is just to demonstrate that the model actually really captures something about the physics of lighting variations. And the reason we want to do this, other than besides having sort of cool generated images, is that we can actually demonstrate that this helps with recognition, right? So the problem with recognition, if you change lighting variations, is that you might have never seen this person under a novel lighting direction, and then that would adversely affect recognition rates. But however, what we can do is we can first remove these lighting variations and compare distances and perform recognition tasks in a much better collapsed space that's invariant to lighting, and that's the reason we get good performance. What I mean by one-shot recognition is that if you were to recognize between different people when you only have one image per training. So, for example, if you're trying to recognize a person based on a passport photo, that would be considered to be a one-shot task, as opposed to having 10 or 20 images of the particular person, which makes the recognition task much easier. Okay, so this so the second model basically covers how do we handle illumination variations in conjunction with the generative model and adding structures that roughly resembles lighting, the way light interacts with the surfaces. What else can we do? What else is left to sort of that cripples recognition? Well, location attention is actually the next big thing. Well, so to motivate why we should use attention is that often images are very big and high resolution, and a lot of times we only care about a small location within the big image. So in this case, we care about the face, and we don't care about the background. Okay, we want to be able to model the face, model the expression, discriminate between different people, doing interesting things. But we don't necessarily care about background, so we don't want to spend the complexity of the model on a background. So what do? Well, we came up with a holistic probabilistic framework that combines visual attention and learning of generative models. So in this case, here's our framework, and I'll show you. And there's a video here. I don't know if you guys can see it, but basically this demonstrates the inference process of this model. So the yellow square is the initial gates. So the model doesn't know where to look initially. So it just chooses a random place within the image. And we have a generative model of faces. Then the attention gets updated every iteration, and it quickly zooms in onto the area of interest, which is the face. And essentially, this sort of this idea of modeling selective attention is inherently existing in this framework. And the advantage of this is that the attention is actually data-driven. So it means that it's where we look next. It's not determined by something else, but it's actually determined by the data, what the image is. So the general model of this model is what's known as a Gaussian deep leaf network. It was used before. Essentially, you think this is a model that can, if you sample from them, they can give you random faces. It learns the distribution of faces. So here, running the video, basically it. So the bottom is the image, the output image. The middle H1, H2 are what's known as hidden layers, and these are binary stochastic latent variables, and they're changing because we're sampling them. We're randomly toggle. So really loosely, they can be thought of as neuron firing, very loosely. But as we run this network, sample from this distribution, it generates faces of different, wide distribution of faces. So this demonstrates that the generative model is pretty good, and it's going to be part of the attention model. So we for this we borrow. We also have something. This is a computational neuroscience model called the shifter circuit by Oshausen and Van Essen. This is 93. There's other earlier work in the 80s by Jeff Hinton on how to do coordinate transforms. But the idea of this thing is that on a retina, things could change in scale and shift around. But for recognition, what really needed is an object-centric reference frame. Up here, you see in A. And then the associative memory or any other sort of learning technique could then just focus on a invariant representation, and not have to deal with different size, rotation, and shifts of the stimulus. So here's our proposed model. So on the right is our model. We have a deep leaf network modeling faces, and the transformation is represented by a similarity transformation, which means that there's a delta x, delta y, the shift in x and y, the shift in rotation, delta theta, and then delta s is the scale. And they interact multiplicatively with the 2D similarity transformation on the image. So we have a model of x of u down this guy's face. And so ours is a fully probabilistic model. Now, this is a proper model, and when you want to do inference, you would just have a big image, present the model with the big image, and it will figure out what the faces are. However, there might be some difficulties, and the difficulties is that if we do inference of this model, it's very similar to some technique in image alignment, which tries to maximize the log p of u given x and v, where u is the transformation, x is the data, the big image, and v is the canonical face. And so what I mean by getting stuck is that if you can see in the video, the alignment, because it uses gradient descent, and we use something called HMC, which stands for hybrid Monte Carlo. The wrong eye gets aligned, and it's hard for the model to jump into the global minimum, which means shifting the template over to the correct nose, the nose, correct on the face. And this is due to the fact that we're using Gaussian residuals, has some energy barriers for HMC to jump out of. So how do we deal with this in practice? In practice, we can use something called a convolutional neural network for approximate inference, so bottom up. And what this does is it allows us to jump into a mode in a longer distance. We're not just doing gradient descent in the energy space of the posterior. So that means our attention can jump many pixels, whereas before it can only sort of do this local adjustment. Now we can make a bigger jump. So what we do is we take the V, canonical image V, and we put into the one stream of the convolutional neural network. And then we take a context window, which is the yellow square as input. This convolutional neural network gets combined. The two streams gets combined. They get multiplied, and what we get out is the new attention. The new attention can then be fed into the transformation U, and then the box gets adjusted. Okay. And then we repeat this process for a few times, and you see that the square gets shifted onto the face in very fast. So that's what's known as approximate inference. So it's using a second network to do bottom up, whereas the generative model tends to be top down. Now, after that, we can then use hybrid Monte Carlo again to make fine adjustments. So So we have a model. We have a way to do approximate inference in an efficient manner. What is next? The next is learning. So to make it truly like the way human learn, right? Is the goal is not to simply do face localization, because that would be the job of face detector, but the goal is to have a generative model framework, that can both detect localized faces as well as learn from faces of a new data set. So the idea here is that if you give another novel person, that's the neural network have never seen before, we want to be able to focus on a face and then learn the distribution of this novel person's face. And so what we do is we use the statistical technique called the expectation maximization, where so it's a two-step process. There's an E step and there's an M step. In the E step, we sample the posterior over different locations. So it's like a face detector, as you see on the right. And after that, we can then update the parameters of the deep belief network that I showed you guys earlier, to allow it to update the model to include this person. So that's what we want to do in learning. Okay, I'll show you this. So this is the example of learning. So first there's two data sets, the Caltech face data sets, and there's the CMU faces. So they're data sets with two sets of different people. What we can do is we can learn on the Caltech faces, and then so that's samples from the model trained on Caltech faces only is on the left, and that's sort of the sample, that's the distribution of what people look like from Caltech. And then what we can do is we can then learn from the 90% of the CMU faces. And by learning, I mean that just feed in a big image without small crops of faces, right? Because that's, with Facebook, with other sort of online media, all you have is these big images. You don't have, it's expensive to actually have cropped faces. So with our attention model, we simply feed in a big image, and the model simply then figures out where the faces are and then learn the distribution of the face in part of this probabilistic framework. And so after learning these, on the right, these boxes of which are highlighted in green, these samples come from the distribution of the CMU faces. The rest are still from Caltech faces. So this demonstrates that learning with this model will allow us to actually learn from. After learning, we have the model can generate samples from both distributions, right? So it learned, it was able to learn from both CMU and Caltech faces. Okay, so I'll show you some more inference examples. So on test images, these are Caltech images, right? So how does inference actually work in this model? So you can see that we can randomly initialize it anywhere, different size, different rotation. That's the yellow box. And as time comes, we're able to zoom in on the face. So that's these are some test images that our model can do. Okay, and so one other thing is that with this model, it's a generative. Okay, so the question is, how fast does it take out what the faces are? So basically, it can be done in real time, because the expensive part is the approximate inference using a convolutional neural network, but it's actually not very big. I showed you before, it's about, sometimes the layer has roughly 64 filters to 32 filters. So it can be done in real time. We're cropping images of size 128 by 128 and you feed it up. So it's really fast. Okay, so the other thing is that inference with ambiguities. And so unlike other face detectors that like the Viola-Jones, the AdaBoost detectors, where it just detects all the faces within the image, this model here is a probabilistic generative framework. So the advantage is that what the V here, the latent V, is, you can think of as sort of the internal representation in the model. So what the model has in mind, sort of. And so everything else in these two examples, left and right, are the same. So The input image is the same. The initial condition, the yellow box, is the same. Everything is the same. The only thing that's different is the V, right? So initially we set it to be the person on the right, in the left panel. And if you do this, the attention will focus on the person, the subject on the left. And the reason it does this is that this will have a higher log probability, right? Because the V matches better with if we focus on the left, and vice versa on the in the example on the right. If we set the person, the male subject, we can then the model easily will drift over to the right, and everything's done in a publicly kosher way. Okay, so that's the attention model. So in conclusion, I talked about 3 different models of how we can actually push recognition beyond simply discriminative training. So discriminative training basically is you give an image, it does classification. It says that which classes are here. So that's discriminative training. The first thing is the robust. We have robust Poultry machines that can handle noise inclusion by using multiplicative gating to gate off noisy areas and fill them in. We have a deep learning Bayesian network that can model beetle and surface normal and do crazy, amazing things with lighting variations. And then finally, we have geometric transformations that roughly loosely correspond to visual attention that allows us to focus and learn general models of object of interest within a big high-resolution image. And so these are just the 3 domain-specific models that use domain-specific knowledge in vision. Obviously, there are many more possibilities for future research. So with that, I'd like to thank you guys, and I will take any questions that you might have right now. Sure. Thanks everybody for attending. You're welcome. Okay, question. How well these models work with various face orientations? So face orientations is, I'm assuming that you're talking about in-depth rotation, so this kind of rotation. It does work, it doesn't work, it works, it doesn't work as well. And due to the fact that this is a highly nonlinear transformation, right? So that's actually a really excellent question. And one thing that sort of as part of the trajectory of these kind of model, which is basically adding structure to generative models, is actually moving to 3D. So 3D CAD models, now we have ability to have using connect depth cameras. We can have very cheap 3D model, 3D data sets, RGBD data sets. So we're moving toward there. I have a paper called Tensor Analyzers where there's some more examples on how experiments where you're actually learning multiplicative interaction with 3D rotations. But the problem is that none of the Lambertian network model, the generative model is actually piecewise, sorry, not piecewise, but element-wise multiplicative, right? So it's every single pixel you multiply by the surface normal with the lighting direction. Now, when you have 3D rotation, it's not going to be element-wise anymore, right? So when you have 3D rotation, you need to actually do the 3D transformation in 3D space, and you can do that with 3D model, but that's for future research. Okay, so next question: can we implement inversion models without data dependency? Yeah, you can. So the Lambertian model basically just says that I have a surface, I have a lighting direction coming in from this anywhere, and I'm going to take the inner product of the light and the surface normal, and then multiply that by a albedo. So the thing with data dependency is that what I really want to do was to do posterior inference with one single image, right? So just look at an object of arbitrary lighting orientation and try to figure out what's the albedo, what's the surface normal. So if you just look at one pixel, right? If you're giving one intensity value, like from 0 to 255, and you have to figure out 4 numbers from it. 4 numbers because we have one scalar for albedo, and then we have 3 numbers for the surface normal. That's an ill-posed problem, right? Because many combinations of 4 number, when you multiply together, can generate the intensity. And so if you have an ill-posed problem, what you have to do is you have to have a prior, right? Prior says that, oh, I prefer albedo to be certain value. I have this Gaussian distribution of albedo. I have another distribution over the surface normal, like so typically surface normal point into the screen and not vertically or something like that. And so if you have that prior, then sure, then you can use that to solve the ill-posed problem. And we use data to learn the prior. Now, if you just happen to know that prior, then that would work the same. But that's where the data dependency comes from. Okay, so next question. Is it possible to apply these models on mobile and does processing require better hardware? Yes, it is possible. So the good thing about the neural networks and machine learning in general is that if you have less processing capabilities, let's say that on mobile you only have 10 watts, these sort of GPUs, the Tegra GPUs from NVIDIA, then what you can do is you can actually make your model size smaller. If you're doing inference, you can do it. You don't have to do 10 steps. You can do it for 3 steps. So we can do it on mobile, and there's ways to optimize as well. I mean, a lot of mobile nowadays comes with. Let's just take the Tegra for example. You can actually, it runs Ubuntu. You can actually run full CUDA on it. But yeah, better hardware is obviously would obviously definitely help a lot with the processing requirements of a lot of these algorithms. Yeah. So let's see here. Next question. It's possible to do what you did in Kaggle in mobile. So yeah, I mean, yeah. So if you look at the so for the Kaggle challenges, it's using a convolutional neural network. Same thing. You can do instead of using filters of 64 per layer, you could use 8 or 16. Instead of using 64 by 64, that's the initial resolution, you could use smaller, 32 by 32 or so on. You can have a smaller hidden layer for final classification. Lambertian models for indoor scenes. Yeah, so so the Lambertian model for indoor scenes might require more research at this point, and the reason is because for faces it's roughly convex, and that's what makes Lambertian modeling easier. Lambertian model is not good to deal with cast shadows, right? So if you have lots of shadows, it's not good because shadows are not generated by simply doing inner products between the lighting direction and the surface normal. Lambertian models also don't do particularly well with specular reflection. So it means, for example, something shiny like the light from the glasses, right? That doesn't handle that well. There's something in graphics called the Fung model, which handles that. So for indoor scenes, you can do a lot of sort of surfaces can be modeled by Lambertian on a smaller scale. But if you want to model the entire scene, there's some with the model I described, there might be some difficulties. In the first thing is that we need to be able to have a really good generative model of the entire scene, right? Which is hard to do currently. We can have generative model of a part of the scene, for example, like objects, and then you have to try to maybe stitch those things together. That's one way to do it. But currently it's not easy to apply to the entire scene. Okay. Sure. Yeah, you're welcome. Okay. Do we have any other questions? Feel free to ask any questions. Sure. Okay. Well, with that, thank you guys again for attending, and enjoy the rest of the conference. Okay. So we have another question here. Specular reflection. Yeah. Like so. So like the Fong model, for example, handles it. There's a coefficient with highly nonlinear constant interaction that handles specular reflection. And that gets into more of graphics. So if you're trying to do computer graphics, you're trying to generate games, for example, and that they do a really good job with that. But again, it's this is sort of like machine learning is on one side, and you have graphics on the other. So some people have theories that says that machine learning is essentially it's inverse graphics. So you want to have start with a graphics engine that goes from high level 3D representation to the pixel space, and then machine learning or perception, just trying to invert that. So given the image, how can we find these variables? But machine learning is a trade-off. So what works well with convolutional nets right now is that we don't really want to model it in a very detailed way. We just want to be able to train something that does something approximately correct. And the reason is that it's too time consuming. It requires too much on hand engineering and to do that. So you have to think of a trade-off as well. And you have to try to strike a very good balance between the two. Because it's too sort of laborsome or laborious to sort of make these details, right? So because if you make it for specular reflection, that might work for certain cases. But what happens if there are other sort of other variations, right? If the surface is other sort of noise happens, like occlusion or there could be other things that might possibly exist in the environment, right? Like snow or rain or something like that. So then the thing is that you want to meet it halfway, right? Like with these huge illumination variations, the Ambrosian model can do maybe 70% of the way, right? And then the rest we just let the bottom up the neural network figure out roughly what it is. So it's all a trade-off. You can model it more accurately, but at the cost of more time spent as an engineer to programming the model and performing inference. How do I handle reflections from bright objects? Do you mean different light sources, or do you mean the light source bright objects, or do you mean light sources? Okay. So with the Ambrosian model, you can add, if there's multiple light sources, we can add multiple lights and things combine additively. That's one way to handle it. Now it doesn't, yeah, so when you have reflections bouncing off different things, yeah, we can't really handle that well. Basically, we treat it as ambient light. So that essentially adds all the pixels in the environment gets added a little bit in terms of ambient. And the other question is that you need to take it do this ray tracing for graphics because you want to generate really realistic looking images. And the question is for perception, do you really need to model it that accurately in order to do a good job in terms of perception? Because it's unclear at this point. What your advice is to hide our faces from AI? I mean, I think it's an interesting question. It's hard. It's really hard because there are some papers published now that's showing that face recognition performance is reaching human performance. If you're allowed to have, if you're trained on database of millions of faces, where for every subject you would have hundreds, thousand faces examples. So for Facebook, if you grab every photo you've uploaded, you grab 100 faces, your face. From that, I can figure out what you will look like under all sorts of different conditions. And from that, then it can actually do a really, really accurate job of recognizing you from now on. So, I mean, I guess just try not to upload as many faces on, Facebook or Instagram. I mean, that's one way. But yeah, it's face recognition is a relatively simple problem compared to general object recognition, and so yeah, I don't mean wear disguises, I guess. That'll be another traditional way of dealing with it. Sure. You're welcome.